Welcome to The Explainer. Today, we're going to crack open the code behind something we rely on every single second we're online: digital trust. What even is that, really?
Every time you open an email or check a message, you're basically making a leap of faith, right? You're just trusting that what you see on your screen is exactly what the other person sent. But think about it. How do we really know? In this digital world, what's stopping someone from just intercepting that message and changing it?
Okay, let's make this super real. Picture this. You send a bank transfer for, say, 10,000 rupees. But somewhere along the line, an attacker grabs it and just adds a single zero. Boom. Suddenly, you've sent 100,000. The consequences of that? They're massive. And that right there, that's the core problem we're trying to solve with digital trust.
So to tackle this problem, we need to be clear about our goal. And that goal has a name. It's called data integrity. Honestly, this is the bedrock. Everything else we're going to talk about is built right on top of this idea.
So what is it? Well, simply put, data integrity is the promise that your data is, well, pure. It's the guarantee that whatever you're looking at, a message, a file, a transaction, has arrived in the exact same condition it was sent in. Nothing added, nothing taken away, nothing tweaked. And that's the crucial thing, right? For data to have integrity, all three of these things have to be true. Not a single byte can be messed with. So no extra zeros on our bank transfer, no deleting important words from illegal contracts, and definitely no changing numbers on your medical records. Okay, so that's the goal. But how do we actually do it? How can we possibly check if a giant file has been changed in some tiny, almost invisible way? Well, we use this really clever tool called a hash function. And the best way to think about it is that it creates a digital fingerprint for our data. So a hash function, it's just a mathematical recipe, an algorithm. You can feed it anything, a single word, the entire text of a book, even a full movie, and it'll chew on it for a second and spit out this unique, fixed-length string of letters and numbers. That string, that's the hash. And the wild part is, no matter how big the original file is, the hash it produces is always the same length. And here's how you actually use it. It's pretty straightforward. The person sending the data first creates that digital fingerprint, the hash. Then they send you both the data and the hash. When you get it, all you have to do is take the data they sent and run it through the exact same hash function yourself. If the fingerprint you create matches the one they sent you, boom! You know for a fact that the data hasn't been touched. But here's where the real magic comes in. This is what makes hashing so powerful. These kinds of hash functions have something called the Avalanche Effect. And it means that if you change the input data even a tiny, tiny bit, the hash it produces isn't just a little different. It's completely, totally, unrecognizably different. And this is a perfect example of that effect. Just look. The original input is "Hello World." And you can see its unique hash right there. Now, check out the modified version. All we did was add a single exclamation point at the end. That's it. But look at that new hash. It's not even close. It's a completely different jumble of characters. This is why tampering becomes so easy to spot. It's impossible to hide. So hashing is amazing for knowing if something changed. But there's a missing piece, isn't there? It doesn't tell us who sent the data. For that, we need to level up. So let's talk about the next piece of the puzzle: digital signatures. Okay, so a digital signature takes everything a hash does and adds more layers of trust. It gives us three big guarantees. First, integrity, yep, just like a hash. Second, authenticity. This is the part that proves who the sender is. And third, something called non-repudiation. And this one is huge. It means the sender can't turn around later and say, "Nope, I never sent that." It's like a digital, legally binding promise. So how does this work? Well, it actually starts with a hash, same as before. But here's the twist. The sender then takes that hash and encrypts it using their private key. Think of this as a secret password that only they possess. That encrypted hash, that is the digital signature. Now, when you receive the message, you use the sender's public key, which is available to everyone, to try and decrypt the signature. If it works, and the hash inside matches a new hash of the message, you've just proven two things at once. One, the data is unchanged, and two, it could only have been sent by the owner of that secret private key. Let's put it this way. A hash is like a tamper-proof seal on a box, the kind that breaks if someone opens it. It just tells you if the box has been messed with. A digital signature, on the other hand, is like that same seal, but it was also stamped with a unique signature that only one person could have made. So now you know if it was opened and you know for sure who sent it.
This is a perfect analogy. Think about an old medieval letter with a wax seal. The unbroken seal itself proves the letter hasn't been opened. That's your data integrity, your hash. But it's the impression of the king's signet ring in that wax that proves it actually came from the king. That's the authentication, the digital signature. It's amazing, right? We've basically just digitized a concept that's been around for centuries. Okay, so let's pull all these threads together. What we've been talking about here, these are basically the three fundamental pillars that hold up our entire system of digital trust online. And this chart really lays it out clearly. You've got data integrity. That's our goal, right? Keeping the data unchanged. Then you've got the hash function. That's the tool we use to check for any changes. And finally, the digital signature. That's the ultimate guarantee. It uses the hash to confirm integrity, and it adds that crucial layer of who the sender is. So why does any of this really matter? Well, because without these pillars, our modern digital world would just fall apart. I mean, think about it. Secure online banking? Totally gone. The privacy of your medical info? Nope. The trustworthiness of academic records? You couldn't rely on it. Even a massive technology like the blockchain, its entire foundation rests on our ability to guarantee these exact things, integrity and authenticity.
But here's a final thought. These tools were really designed for a world of human-created data. Now we're diving headfirst into an age of AI, of deepfakes so real you can't tell the difference. The very idea of what's authentic is getting blurry. So the real question for all of us is, how do these pillars of trust need to evolve? How are they going to keep us secure in the world that's coming?